immediate roots in green steel production.
That's right. So let's. So I have no presentations anymore, but maybe I can make some presentation later. But what I'm going to talk about, I think we have the three needs. One is potentially charcoal application in blast furnace. Other one is sintering using biochar. I think the gentleman told. And the other one is carbon capture and storage. So three areas I'll cover, about 3 papers we have got. So time to time, basically that's what we'll discuss, and then maybe final session we can have a bit of open-ended discuss what we learned in the last few days, or what's new to you, what's new to me, and how we kind of wrap it up. So that's my plan. So you can see. This is development of low-emission integrated steelmaking process, and that is Journal of Sustainable Metallurgy. So Dr. Sharif Janshani, John Matheson, Dr. John Matheson, he was a R&D head for Blue Scope that time, Blue Scope Steel. Somerville is my colleague, myself, you can see that the other colleagues we developed together. So that's the Journal of Sustainable Metallurgy. That's the, I think there's a volume 1, number 1. 2015 that journal started. It's I think it's by TMS maybe. This is the Mineral Society, and actually now the editor of the journal is Professor Uday Pal from Boston University. That Boston Metal very there connected, and Professor Akbar Ramdhani from Swinburne University. And actually I am also one of the associate editor because I have not done last few couple of weeks. There are a lot of papers come to us, and we kind of see that from the publishable, whether that can be sent to review or things like that. So I'm now part of Journal of Sustainable Metallurgy. I'm in the editorial panel. So now, so we published it was quite big article, long article. So development of low emission integrated steelmaking process. So what I'll do, Avash, you take all these ones so that everyone can get access to that. It is accessible by the databases, etc. But some people might not have access to database, so you can probably add this one. This is our author's copy, I believe, so I think it should be fine for educational purpose. So you know that's all intro, etc. So basically these questions like that. So I don't know whether it can be seen from the back, maybe a little bit difficult, but you can read it yourself. Can deep cuts into CO2 emission be made using current processing equipment? Can charcoal provide a low capital path to a low CO2 future? Can waste heat recovery from molten slag provide a further cut in CO2 emission? Can dry granulated blast furnace slag be a good substitute for Portland cement? So these are the assessment when we talk about what are the opportunities without changing, and we're talking about 10 years ago. So must be this is still valid, I believe. So sustainable supply of biomass, utilization of charcoal. Yesterday I showed a little bit. Recovery of high grade waste heat and conversion of molten blast furnace slag to kind of Portland cement type product. You can, I don't know, you have a slag, right? You do granulate or water granulation? What about the uniformity of the distribution of the particles? Is that good or is that reasonable, acceptable? So in our process, it can be more precise in the particle distribution because it's dry granulation. So yesterday I showed you the diagram so that in Australian condition, because we have got lots of land, biomass, agriculture industry, forestry industry, where that biomass we can even farming, we can farm biomass and then put in the energy system, we can get energy to the steel plant or we can get renewable fuel and steel smelting, granulation and then cement production. So that's sort of conceptual also for the low emission integrated steelmaking process. Then one other thing I think I want to highlight that where the opportunity, I think yesterday we discussed about global warming potential of kilogram per ton of charcoal and where they're coming from and what is the net CO2 per ton of charcoal. And this sort of diagram you can see. I showed yesterday 100,000 ton of charcoal, 20,000 ton of bio oil, and you need 500,000 ton of biomass in that sort of scenario. So yeah, this paper will be given to you. So that's 100,000 ton. Now what I was going to show, I think we costed, we saw that on how much that ton of charcoal gross operating cost. One other thing I like to highlight that that raw biomass cost. We had $200 per ton of biomass. What? I'm not sure. Maybe in India it's been low. It could be cheap. I'm not sure because in Australia we're talking about biomass collection, processing, before putting the biomass plant. So that's the cost associated with it. So if it is lower, say this cost may be half, then your charcoal production cost is getting cheaper. So those sort of, and also labor cost is high in Australia. So those can be taken into account, and it could be lower in case of India. So if somebody can do this sort of assessment, I'm happy. So you can see that charcoal properties, somebody says that what about ash, charcoal actually low ash, low volatile matter also I believe. So but you can see that pros and cons. As I said, that about 10 years, more than 10 years, actually 12 years, so a decade, many scientists work, many people work, and that was the outcome. So it is and no one in the world, I don't think no group did that work in that sort of comprehensive way. So basically it is publicly available, although some of the internal information we share with our partners, but we also publish it at least what is publishable. So you can see that when integrated blast furnace route, that what's the potential possibility, and electric arc furnace mini mill route, what's the possibility of CO2 reduction using charcoal with credit, without credit. So we discussed that yesterday. So I think one thing I would like to show, that is our reactor, and I showed briefly that wood chip goes to a dryer. Okay, so it is happening. You see that wood chips going into dryer to conveyor, and that in our reactor hopper, and you get charcoal, and then all this system are cleaned up in that. So it's a self-sustaining process. It's a residence time 1 hour. Basically 1 hour dry biomass, bone dry biomass to charcoal. Within 1 hour you get charcoal or biocoal, which takes millions of years underground to make coal from the fossil energy, And that was obviously in this case we are using wood chips. If we talk about fossil coal, that's also wood chips. Biomass is under pressure and temperature for a long time. It's the same process. It's artificially enhanced. And I know that Fraunhofer Institute in Germany, they have a similar kind of process, but I'm not sure where they are. So this is our equipment we develop, and this is a kind of I think few kilogram per day, a ton per day of charcoal, something like that. That's our production scale. So, but again, the cost issue, the carbon tax was withdrawn, and that was a problem. So I think the purpose of my showing this one, I'd like to show you where the biomass can be applied in terms of blast furnace scenarios. So I think yesterday I showed that on the net reduction, significant reduction is possible with credit and without credit. So that's right, but before, this is a table I was going to talk about. So it's a little bit difficult from the back, but you can see the application and then optimized quality parameters, and sometimes charcoal needs a bit of treatment, net CO2 savings, and what is the current status, what is the next step. So sintering solid fuel, coke making blend component, you can have say 5 to 15% sintering fuel can be from biomass. Coke making blend maybe 1 to 5%. Blast furnace lump charcoal charge 1 to 5%. Nut coke replacement 3 to 7%. Carbon or composite probably that's 7 to 5%. Blast furnace pre-reduced feed and 2-year injection 19 to 25%. That was one of the largest. But you need to crush charcoal to make some fine material, and you can probably inject that way. Pre-reduced feed and blast furnace fuel, so that up to. So each of these areas, decarbonizer, and that's obviously electric arc furnace application, 4 to 8%. So it's not 100% you can replace some situation because the fuel needs certain characteristics. So when you said that what can you do with blast furnace without changing it, these are the scenarios probably small scale you can try out and see whether it works. So does that make sense?
Yeah, this data is 10 years old.
This is 10 years old, but I don't think it changes.
There is a trial on large BF for BF injector.
So we didn't go to blast furnace trial, but we did electric arc furnace trial. The trial was successful, no issues. Whatever we expected, more or less in electric arc furnace.
But blast furnace?
Blast furnace one we didn't go ahead because by this time project they didn't want to go ahead because still maybe we can relax, carbon tax was withdrawn. So now people are talking again, and sometimes that we said that this sort of work we did, if we need to do, we have done some theoretical work, let's do, or even laboratory scale we did, to work again. But because we had a large furnace in the kind of ton scale furnace. That was okay also, but we need to industrial furnace. That was the plan, and that needed more money in the effort, and in the meantime, project will finish.
That is 19 to 25%. BF2 are injected 19 to 25%.
That's
That
right.
is laboratory data.
That's the kind of predicted laboratory and tested data kind of that way. Yeah, that's it. Yeah. So, but largest component looks like fuel injection, I think. Yeah, that's my understanding. Yeah. But again, there are density issues, there are moisture contribution storing issues, charcoal is lower density than coal. So those sort of things you need to take into account. And obviously, and then you know the value in use, you have that concept, right? In the steel industry, quite frequently used. So you can see that charcoal value in use is higher. So if you go more up, that means that fuel is better for productivity of the furnace. So and the reasons that you know if you compare with the reference high volatile coal, high volatile A reference, that one. So charcoal is probably at least 80% better. 1.8 the polycharge charcoal from and various wood has got various properties. So it is quite well researched area, but end of the day, industry expectation is probably the cost was that kind of issue. But now, if you know that what is called that your production is more decarbonized, you need to start somewhere, and that could be without. This is without changing any infrastructure. If you want to change infrastructure, then that's another story, and you can do significant blending. So that's a granulation technology we have. So slag granulation. So you basically there is a slag comes at high temperature, falls on a spinning disc, and it moves like that. The good thing is that this happens in a reactor, so you get heat recovered, and very high grade heat, 1500 degree, maybe 500 degree you can easily get. And but the uniformity of the granules, and with no water use, number one. Second was the uniformity of granules is very good for cement production, and it's going to be attract higher premium compared to your current product. So that's sort of product. So water granulated and dry granulated is see the color, and ground dry granulated slag, and that can be used for the cement. So that's basically it. I think that's our standard. Actually, it was the smaller version of dry granulated unit, but we had much bigger, and then this one is transferred to in an industrial operation in China, and that's a million ton plant, nearly a million ton plant. So they're using it successfully, and I think they are the sole agent to, if you want to buy technology, we don't have anything, you have to go to the industry. Okay, any question?
What is the paddle made of? The spin wheel?
What's the made up of?
Yeah.
I think the disc is,
Zero?
yeah, I think something like that, but it's not expensive also. It's kind of if you want to get the heat, then maybe some insulation, etc., etc. But generally the material is just a standard material, falls on heat, and we did a lot of CFD modeling to design it, and as I said, it is already kind of industrial practice. So
This for blast furnace slag.
this is blast furnace slag, but later actually, so blast furnace slag we gave to the technology China. That time we had a good relation. And then COVID happened, so it would become slow. But finally, I know they are implementing it. And the deal is that if they implement, and they will give some royalty, obviously that's sort of deal. But there are a lot of interest now with copper slag and other slag. And I think some tests we have done, it is not impossible, but you need to modify because the slag behavior, as you know, are different, and temperature they come some here. We had a lot of interest in India. Indian companies actually asked us, can we get this technology? But because we get that, we cannot really could do much. And yeah, and I don't know, Chinese and Indian companies probably do not work. I'm not sure that collaboration is strong, isn't it? So probably it falls through. Actually, ST MRI as was saying that one that they were very keen for this sort of technology for India. But again, we're talking about steel slag, maybe potentially other slag that we have not given that technology to China. So maybe that if there is interest in one copper slag or nickel slag or other melting slag, you want to process with dry granulation, that could be another area to look at.
For steel, POSCO has got a technology. Also, EcoMaster of Korea.
Koreans,
Yeah, they have a granulation process.
But is that dry?
EcoMaster.
EcoMaster, but is that granulation with dry air or what?
Dry air. Simply a blower is there and you pour the slag. It is thrown away like 1 mm, 2 mm nuggets.
It's like
Steroids
atomization,
will form
kind of atomization technology.
and it will be exported.
No, can you capture heat in that situation?
No.
No. This our technology has protected that component heat generation and heat capture. So that's what you can see. Very nice uniform. We used to take a lot of video, a lot of fun to see that how what metals fall and then nicely distributed and so the high speed video could take it. So I had a video I can't show you now, but I can locate now. So you can see that lots of scientific information is there. What flow rate, how you spin, what the disk size, etc. So we did a lot of modeling around that, and what's the droplet diameter, what's the distribution. So yeah, that paper is there anyway. So you can what time you should. So quite a bit of operational issues, and you want to be really good way to do that with some costing. And anyway, as I said, it is already in a million ton, 800,000 ton plant. Besides that, there is now. So I hope that they will sell in other places because more people would like to extract heat. More people will be going for water-less processing because water is sometimes problematic, and once you granulate that produces a lot of emissions, if you want to control that, they will be making money in this, and but anyway we will get as kind of royalty apart from that. So that's one. Any question about your blast furnace? Existing furnace, this is maybe looks like a opportunity.
Yes, we need to know the result actually. If anyone has used the
Yeah, so maybe keep an eye with the MCC in plant in China, and I'm sure they will be releasing a lot of information because they want to sell that globally worldwide.
So you made the technology for them or?
No, we get the IP. They are manufacturing is not we do that. So we get the larger version of that. But we had a big demo version. What I showed 10 times more than that we had in our facility. Any question? So that's for you. You said about blast furnace. So that's why I sort of picked this paper. I thought maybe going through that would be useful. I think yes.
So the main advantage of this dry granulation is what exactly?
What is exactly?
So making cement or
Number one is that waterless. Some places water is precious and water slag interacts and some emissions. You can check that one. Second one is that you can capture heat. It is enclosed in a kind of system. Okay. And third is that droplets are more uniform. So these are the 3, 4. You can overall you can get that heat and use some other that waste heat can be used for steam, so supplement your energy, so that overall your CO2 emission goes down.
recuperator they are using to recover the heat or?
Sorry?
Recuperator, what kind of?
Yeah, some kind of there are heating unit and that also cost, but that we have done that looks like it's a pretty good heat because 1500 degree coming and 400-500 degrees you can extract here with some sort of technology. So I think that's one. And the second one, iron ore sintering with biomass. I think you probably asked that one, right? So maybe let's quickly look at. I hope this is there are a few papers, but I think. So iron ore sintering with charcoal. That's my colleague Roy Lovell, Keith Mining, who has been here last green steel course, my boss, and another scientist I think left now. So we did learn for 3 papers. I will just go through what model is very similar. Various things. Sorry. Anyone? Any question? No. Okay. So iron ore sintering with charcoal. So what we did, I think this one I will skip some of the background stuff, but you can look at the proximate analysis. Maybe I'll increase the size of that one. Hopefully you can see that. So that what we tested. Coke 1, 2, char 1, 2, 3 samples, and you can see the ash content between coke and char.
VM is varying in all the 3 samples.
Sorry?
The VM is varying on all the 3 samples.
That's right. So that's the variation char is less than different char. So that's why 3 samples, 3 different food maybe, and fixed carbon you can see volatile matter, dry matter, etc. But ultimately calorific value. But charcoal is not bad really. You can see that 28. Yeah, 24. It's a bit of variation because of the different crude has got. If you make charcoal, some would will release lignin. Some would lignin is high. That will convert to charcoal. That some of the volatile matter are high. So that's why, yeah, we need to know that one what's exactly we're talking about. Say air moisture, etc. So now, if I see that one, so that yeah, so those are basically these were made a lot of sample and characterize all the properties of this material. That's what we do on this fuel. And then finally, you put under the microscope also, so various properties, porosity, permeability, etc. You look at that. And then ore blend, if you look at that one, I can increase a little bit. Obviously, reactivity, one thing, specific reactivity with CO carbon dioxide. And then ore blend ratio, so high ND fines, rope repair fines. Carajás is Brazilian sample, Itabaria Brazilian sample, Hammersley fine is Australian, Mount Kingman is Australian. So this one.
These are iron ore.
No fine.
Yeah.
That is
Yeah. So anyway, so that's one. And to be honest, I didn't. I'm not 200% familiar with this work, but at least I know that. So that we had a big sinter plant, various capacities.
So how much? What is the proportion of coke green that has been
I
replaced?
hope that there are some results will be there. I'm not sure. Summary is entering. This is already summary, so that means coke 1, coke 2. So my feeling is that they had the similar ratio because of coal and material, but they
Specific consumption of coke.
took. I think you need to go through the paper to understand a bit more, and I'll make sure Avash gives you. But essentially, that various properties, sinter properties, they tested after doing sintering, and then that's the various results they got. And I think the main conclusion is that you will see that one that that it is. They think my colleagues think that it is successful. Whatever properties they studied, there are some few bits and pieces maybe up and down, but generally overall, our suggests there is no apparent technical barriers to the replacement.
Tumbler index has reduced.
Sorry?
Tumbler index, the strength of sinter has reduced.
Can you please scroll up?
Okay, so I think you can probably interpret better than me. Let me see. Sorry.
Up.
This one.
Up or down?
Up.
This one.
The tumbler index has reduced from 68
So that's
to
a
60.
63 to 60% is a major reduction. Is a significant and problematic.
Reduction, yes. Return fines will increase due to that.
And that's also problematic, isn't it? Yeah. So I think those ones, but overall, what I find that he says that you can see this one. I'm not sure because I'm not sintering expert either. It says that our work suggests there are no apparent technical barriers to the replacement of coke with wood char in sintering. However, char availability is presently a significant constant for Australian sinter plants, although in countries like Brazil, extensive. Basically, they are saying it's okay, but
Can you come to that graph on the left side? Graph.
So
They are tried with 50% charcoal and 50% coke.
So that's
They have gone all through 100% charcoal also.
So they're gone maybe. Yes, that's what
Pura
also.
ही किया है.
Scenario.
पूरा किया है.
another percentage balance, 0 and 100%.
So,
Why not?
yeah, so at least what I can see,
Different time.
without doing this research or trial, you can access this information. So you can evaluate yourself what they say. But apparently my broad understanding what they said, it is okay. And then we did also costing, we did also technical economy, LCA, that overall that reduces the CO2 footprint quite a bit. Yeah. And that's when we said what sort of percentage of fuel you can replace. So that came out of this kind of research. Okay, so that's probably I want to tell about what I know of. Alright. So you can have a look also there obviously properties study. So it's a kind of systematic study, and I think good whatever way you can do. That's sample take, you characterize, you do the systematic campaign. And our sinter plant was a kind of not a small lab plant, it's quite big plant. Yeah. You need significant amount of material to run the plant. Alright, so
They
there are
tried 100% charcoal in that big sinter plant.
potentially, yeah.
Potential.
No, so I mean whether you can do or not.
They have tried 100% charcoal.
But I don't think 100% charcoal is the result was good, my feeling. So
Because VM is very high, it might be detrimental to their equipment.
So anyway, so that's my kind of, you might need to go into detail if you are interested and see whether you want to do some test, and I'm sure that facilities still exist in Queensland, so you can study various properties of, so it's a kind of complete sinter plant, industrial sinter plant kind of replicated in a lab. So what else I was going to show? So that's the third paper. So there are a couple of more papers on sintering. You can go reactivity study and there are really specific things. I'm not going here because I cannot even explain myself So that's not, as I said, not my idea. So this one, I hope you can see from the back, International Journal of Greenhouse Gas Control. So that's Bharti Garg, who is one of our PhD student did. So the technical evaluation of amine reclamation technologies and combined CO2 SO2 capture from Australian qualified power plants. So I think someone told me, asked me about, is that person still here? That CO2 CCS. Who's told me that about to talk about CCS?
Yes. Yes, sir.
Yes, you told, were you interested about CCS to know more?
Yes, sir.
Someone anyway. Oh, so you told, that's right. So that's the paper. I thought maybe three, and in my mindset, that's the three colleagues wanted some more information. So it's a technical evaluation, but we did a lot of practical work also. But I was involved in supervising this student for the technical meet. And that was, you can see that Carbon Technology Research Center, Federation University, where all the power plants are, our energy business unit, and Professor Vincent, he was the person behind that university. And all of others, my colleagues. Paul Ferron, if you Google Paul Ferron, he is one of the best experts in carbon capture technology around the world. So what we did, we have a patented process. We said that so most of the power plants are disapparition in FGD. So if we do the same unit CO2 capture, what happens? So that's the evaluation. So if we go through that, so we have got a patented, carbon sulfur capture process, we call co-cap kind of. So, and we have our own amine system. So then that, what's the consequences of that? What is the possibility in terms of cost? So if we go a little bit, not too much detail probably, because if I go, so this is the system we're talking about. So if I reduce a bit, hopefully still kind of understandable. So that's the capture plant. And we had obviously pilot plant near the power plant, and so sort of cleaned flue gas is going through the system. That's the, on the left, that's the capture unit. You get lean gas, you get rich gas, and that goes through all sorts of processes. And finally, you get, CO2. That's the top one. That's the CO2 coming out of the system. That's our product, where my cursor is. And that goes to the compression and carry transportation and under the ground for storage, or you can use it. Whereas these two units are more generation of agents, so that you can send it back and you can make some money out of, or make the process can be cheaper. So that's broadly the situation. Now, so that's the system we studied. FGD plus PCC, post carbon capture, flue gas desulfurization. So FGD plus PCC plus our input solvent, and minimal, so without no modification of FGD plus PCC. So this kind of 3-4 scenarios we looked at, and based on some experimental data also. So that that some cases the options are that how you regenerate, you heat it up, recrystallize or something like that. So that's another kind of area. And then what is the we did Aspen class modeling for the whole system we showed, and what's the material, what's the going in, what's going out, what are the species, what phase, and we did for 900 megawatt power plant gross, okay, that electrical for one post combustion CO2 capture train. So that way we looked at that, but I'm going to give you probably the scenarios. Hopefully that's visible a little bit tricky, but let me increase the size a bit. So scenario 1 was base case, retrofitted with PCC, FGD plus selective catalytic reduction, base case with FGD plus SCR, and then base case with minimal FGD plus SCR, carbon sulfur capture case with thermal reclamation, carbon sulfur capture case with reactive crystallization. So these are the scenarios we looked at. And then we had some capital cost, that there is a big program I told you about in the morning or yesterday, CRC. So this was a CO2 CRC, Cooperative Research Center. So it is power plants, universities, CSRO, government gives 50% money and 50% money comes from the industry and partners. It's about $100 million over 10 years. I think this program went even 2 phases, so at least 15-20 years I believe. And still they exist as a company. And they have some of this technology already, they are promoting, marketing, mainly the amine for capture process, not necessarily whole system. So then what we did, we had this kind of number, so that what is the capital cost, what is the operating cost in dollar per year, kind of based on the flue gas sulfur ppm, and where for a specific plant. And then what we finally calculated, but I don't want to go into detail because it's a quite paper you can have a read, but mainly what is the levelized cost of electricity because of doing all this, and that's what we calculated and presented. But all sorts of capital cost was included, that power plant scenario, power plant efficiency, power plant, what I would say, this is coal-fired power plant obviously, and all the information was given into the model, and the model calculates, and we probably later got some feedback from the industry colleagues, and that final result what I would like to show, I think maybe there are all these numbers are there, but this is the levelized cost of electricity, that's the result. So basically, if I increase a little bit, hopefully that is still visible, because too much if I do that, then that will be not visible. So what we are saying, the cost average dollar per megawatt hour. Okay, so that's your axis, I think visible. These are the scenarios we discussed, 1, 2, 3, 4, 5, I think 3 maybe, this one is not showing here. And you can see that black coal power station, 450 megawatt, and brown coal fire, 2100 megawatt. So when you do that one, so that's the overall cost per megawatt hour, 133, 152 for brown coal, 129 for black coal, scenario 2, so roughly you can see that 140 plus minus. So that's why I said yesterday that what is the CO2 capture cost. So this is kind of, that is kind of 10 years ago or at least 6-7 years ago. Where I doubt that number changed too much. So it would be even maybe cheaper potentially because process become more efficient. A lot of people are using this kind of technology are considering. So maybe $100 mark I would say. Yeah, not less than $100 I would say. So but there are other options we have done and looked at. So I think this is what I wanted to show you. Basically that's the result. So any question from you, or do you think that makes sense from your point of view? So your sulfur unit, same unit can be used for PCC or minor modification. You said that plus minus cost is $120, $140 ballpark per megawatt hour. Any question or comment for our power plant colleagues? So here FGD is there, right? Most of the power plants have got FGD. Eh?
We are about to install it.
FGD.
Yeah.
So do you think?
Sir, I had a question.
Yes.
For installation of FGD,
Yes.
we are also producing CO2, which is I think more than the SO2 being reduced.
Yes.
So
Maybe because you are using power for that, or that's why, or also during the process, during the reaction process,
Yes.
CO2 is generated.
Yes.
Byproduct is gypsum and CO2.
So I think this unit they are talking about sulfur, and at the same time maybe with that HGV plus some another unit we capture CO2.
But that we don't have. For capturing, we have nothing over there.
So maybe your HGV is kind of another technology which will just only
Reduce the SOx. But in that process, we are releasing CO2 also.
Yeah, so that maybe then capture another way and you have to do something like that.
There is no problem with CO2.
So that
With FGD, no problem for capture of
CO2, you don't do anything, just only SOx, because that what's the limit? What's the
Depend on the power plant of when it was installed.
without installation? What's the SOx?
Like for us, it is
465
for 55 ppm, and with
and
unit,
after
it will be zero.
30 or 30, 40.
And what's the target for government?
200 mg per annum.
If that goes below, that's fine.
Very much good.
But we are reducing up to 40.
And what sort of investment we're talking about if you don't mind? If I agree,
531 crore. 531 crore.
it's $100 million.
So 1,000 megawatt.
$100 million plus dollar, right?
Yeah.
So that's and that will be for the whole power plant, right?
No, for 1,000.
1,000 unit, I see.
500 into 2.
So I think because there is a huge pressure to reduce SO2 and it's a government requirement, right? We have to do it. But CO2 maybe another matter later when that direction comes, then maybe you have to need another one. Maybe you can now think of if you do two together what happens.
इंस्टॉलेशन के पहले एसओटी के बारे में सोचे थे
Sorry?
इंस्टॉलेशन के पहले एसओटी के बारे में ध्यान दिए और जब हो गया तो सीओटी
Oh,
को
yeah,
आगे
that's
से
right. That's right. That's right.
In Indian code, there is very less amount of
Sulfur is not much.
Yeah.
But still you have some sulfur above limit.
Yeah.
Planning was to use the foreign coal.
Oh, I see. But foreign coal is making some.
Australian coal actually, Australian and Indonesian.
Is it? Indonesian coal. I understand Australian coal has low sulfur. Depends also because our Queensland coal is problematic. I know. I mean, on New South Wales has got the sulfur, whereas coal in Victoria, which obligated electricity was very low sulfur.
Australian heart is there.
We don't need to use because that's not going beyond cost.
Initially they already producing CO2 by combustion
Right.
of coal. Plus after the installation of
It's added more.
adding more to the global warming.
So unfortunately that if you don't have any pressure, maybe you can get away as long as that direction comes. Maybe when carbon.
The reagent used is limestone.
Right. So now, say next year, I'm not sure, hopefully that will not happen, but say India has a carbon tax, what would you do? Carbon tax. Say if the government impose carbon tax, and you know 1 megawatt electricity will have 1 ton of
We will
carbon.
calculate the
How much manipulation will
How come you can do this? Say 1 ton, maybe half a ton?
Then they will more trees to capture that.
So anyway, so it depends on how much carbon tax must introduce. Maybe $10 come, maybe the people bother. Another 20, maybe not problem. Maybe 30, then you can manage this thing, isn't it? But if it says suddenly power price goes per megawatt hour by 50 or 100, that's the problem, isn't it? That will not be profitable. So then something you need to do, you have to invest maybe some technology, etc. Okay, so this is just I want to share. Makes sense? Everything okay? Any question if you have? If not, let's move on to the So actually what I do, I know you have to have a quick exam, but not necessarily I'm going to give the exam, that question is not question. But what we do, this kind of thing, what is in this one, I'm trying to figure out myself what we really do. What are these inputs for? Think, can you imagine what we are making here? So it's still making, are we still making, right?
Yes.
Because it still needs diesel. Why
No,
is
it's
it?
written on the left side.
Yeah, that's right. So those are items. So items require diesel. You need diesel. Where is the diesel?
For transportation of ladder.
Maybe transportation, maybe in the mining, in iron ore, maybe. What about coal? Yes, that's
Coal is
I bet it more high, isn't it? So it's 500.
no, the coal will be
Because
coal
there
will
is
be
no carbon.
580.
PCI, all the coal will be
580.
580. Whatever carbon in whatever form, it's 500.
Coal is 580.
580. That's right.
Coal.
580. So I'm right.
Yeah.
What about electricity? That's the number anyway. You cannot tell me, but I can tell. Does that make sense? That number? Plus minus ballpark okay or not? Too bad to good.
It was 300 around here. 310, 320.
320. Right, so 289 is whatever. Limestone, is that number right? You don't use flux, you said, is it? Or less flux?
You don't use like.
So it depends on what way. It's one way of making, because maybe your way is different, but this is one data.
No, actually this was steel, so it will
include everything. I think from raw material to the
So
steel.
steel, yes.
So that number could be right because in SMS also they use limestone. Calcine lime is also
Some other use, yes. And you use dolomite also?
in the plant.
Dolomite.
This is up to crude steel.
Dolomite
This
is
is
a
from yeah, from first to finish, last product.
Dolomite you have used for that.
And oxygen, is that oxygen number right?
78 kg per ton of water. तो SMS वाला पता नहीं है ना SMS तो जो लास्ट फंड वाला पता है
Reasonable, right? It's a low end. Maybe 100 kilograms, is it?
it's higher.
So you maybe 60, is it? Or something like that?
Yeah, you got 50 around.
Required is more. You are capturing low.
So, but anyway, that data I don't know where I got from. Obviously, not, I know exactly where I got from.
I don't know, it should be, as per our calculation, it should be around 170.
So it's a kind of generic number, I just because of the
Yeah.
exercise purpose I give you. So now, my question is that what is the total carbon footprint of the steel? So what you need to do? First you need to raw material, how much it is used, what is the unit per ton? So my question is that per ton of steel, what is the carbon footprint? We should be able to get it, right? So now the main factor is that main number is characterized. So if you know that one, nowadays you know that Singapore software, I will show you that also. So because one of the sessions is that how to calculate is steel CO2, right? That next session we're talking about. So if you know how much is going in, and if you know what is the characterization factor, and unit is kilogram CO2 per load, diesel is 0.7 kilogram CO2 per kilogram. Okay?
It's a 0.7 comes. Our footprint for
Times
diesel.
that, yeah, just times that, isn't it? Yeah. Same way, I think everything kilogram per ton, and these are kilogram per kilogram. Yeah, I think I maybe mixed up with units intentionally to confuse the students. Sometimes they get confused. So I gave the kilogram per ton, whereas here I gave kilogram per kilogram, right? That should be kilogram per ton, isn't it? And then you multiply. So it is a very simple question, but I think let's do that for multiplications.
One should do for the practice.
So if we do that, that times
Cross 0.7.
that, and if I all these ones
Out of one.
and sum,
Equal to
Multiple marking is wrong.
What are some people?
that's wrong, right? Is it wrong?
1951.
Oh, no, right.
No, it's right. 1.9 per ton.
Yes.
So kilogram CO2 per kilo per ton of
Per ton,
steel.
per ton.
It's right.
Now right, isn't it? Eh?
Yes, right.
But sometimes I make some unique mess up and give it to students to get confused. That's way to reduce mark. And if you have a bell shaped anyway, so that's one way. And sometimes I say another question that say that so you see that electricity. Everybody understand this calculation? Any mention anyone?
How can this characterization factor?
How do you get characterization factor?
Yes, sir.
That's the software, that's the people have generated. Nowadays you can get online lots of characterization.
Regarding
There must be some theory.
Sorry?
There must be some theory for calculation of.
Exactly. That's the one IPCC. There are so many life cycle assessment I said. So 20 years people probably have the career to develop characterization.
Yes, and it is also easily.
390 to 400.
But nowadays you get easily. When I started my career, it was very difficult to get.
This is the average data. Data was 20-30 years. This is generated.
Yes, that's right.
the gas price is based on the Kelvin square.
No, that's for example, coal characterization factor. You can see how much carbon is reacting how much CO2 generated, that's for the reaction.
You said, say for diesel, you know the carbon percentage. You generate CO2. You get total tonnage of CO2. You divide it. You get the calculation factor.
Another thing, my feeling on the diesel one, 0.7 kilogram per kilogram, I think is low. Reason is that it's a diesel making. You know, extraction of oil, it does not take into account the combustion. If you add combustion, that will go. That will be problem too. That's a mistake. Sometimes I say, what is the wrong here? And the student will say, if you understand properly, they will say, oh, diesel is not right. It's only the fuel. Remember, I had a fuel preparation, fuel combustion. That's a good point, right? So we are on the same page, right?
Because if all the data were correct, that figure would have been around at least 2.5.
So now tell me, because that's where diesel was missing, that's why. Now tell me, say electricity, I asked that question because this is a all not question. I say one A, B, C. So first I give the data and A, calculate the footprint. B, say that electricity I replace with solar. Okay? Electricity I replace with solar. So then 1 will be very low, right? 0.1. 0.1 or 0.2. So let's do that one. So let's see that solar as a 0.1 instead of 1. Even good solar. So that's reduced. And I say what percentage of reduction possible?
That's why we are aiming in the electricity only right now.
You see that one?
At least it is 5.2.
So what say I will say that electricity.
It is full.
What else I can change? Maybe gas, but we don't maybe big then. Maybe what about coal?
Biomass.
Maybe I say here instead of coal I put hydrogen.
Biomass can be.
How much hydrogen I need to put then?
Biomass.
Say 58 kilogram per ton, because the hydrogen is more energy dense. And the factor of hydrogen, say we saw that one, right? The clean certified hydrogen, 1 kilogram per CO2, right? See that?
500.
ज़्यादा ही कम हो गया।
It's 0.5 sir.
Which one? Sorry.
Some is 0.5 per kg.
Super green steel.
Which one are you saying? There is speed. Which one?
502.
This number. This
It will
number
be
is
super
possible.
good.
You will be promoted to head of the government.
1/5.
Just go and tell and get a promotion at least. So anyway, so this is the way. If you have a model, you have got some tools you can play around. So basically, that's the point. Yes.
12 gram carbon
Keep on going.
12
gram carbon
44. Because 12 by 44. Yes.
Yeah. So if you assume that 100% conversion, then it comes around 2.6.
Yes.
But what data you have given is 2.6.
Yeah, I before I think. Yeah. I think let us see the point. Why is that one which? Any idea?
Maybe we are assuming that 100% carbon converted to 100%.
Not 100%. That's number one.
But in blast furnace, there is no so whether this good feed, we are only considering
Right, yeah. So that's right. And not only that, maybe they will capture some CO2.
No, the image will be reduced because that blast furnace gas is being used to produce electricity. So we get credit in that way.
Right.
So it is being used as a fuel in other departments.
Yep.
So that is being replaced in a positive way. That is decreasing itself.
That's right. Yeah. So as I said, this one would be 0.2.5 I put again. So that will be what anyway, diesel is not much because that's another sector. So anyways, that's one thing. I'm not sure what I'm doing. Is it, anyone is here aluminum making? Any understanding or familiarity with aluminum? So diesel, carbon anode, electricity from black coal. You need 16 megawatt hour per ton of aluminum. This is huge amount. Aluminum chloride, cryolite, aluminum, acid gas. So again, I said based on the above, what is the throughput of aluminum? If electricity is generated from solar or some low factor reduction, and what is the reduction percentage if you hydroelectricity versus coal? So that because a lot of aluminum production in the world, it is because around 20 can potentially be reduced by 77% to 4-3 to go for hydro, switch from coal to hydro. And that's why you can see the biggest aluminum productions in Norway, Canada, some countries in Australia, we have got one plant on hydro electricity. That's the benefit, or renewable, or some other sources which is not as, because we use lots of electricity.
Electricity is huge required.
Because aluminum is a electrolysis process, isn't it? Have you been to an aluminum plant?
No, not yet.
Very interesting. I mean, they have big carbon rods and then drop like that and use electricity from the bus bar come and to basically electrify the material and then aluminum is melted.
All for the base.
It's a kind of electric arc. They call it electrifying. And then carbon anode is dissolved.
What process is asked for this?
And sometimes the parts can go to carbon parts, they make more anode, etc. Quite interesting aluminum also. So anyway, that's another industry. Any question or any comment? So I don't know. I think, do you think if you go back, you should have some sort of model like that and some sort of expertise like that, or the new engineer you employ and train them up to do this kind of thing? Would that be
Not trained. We are not expert that we can train anyone. Not that much expert.
You are already expert. Exactly.
We are not that much expert that we can train someone.
Oh, I see. Okay. Right. But you know, you can dedicate someone. They can get training, sent to that.
LCA.
Yes.
This kind of simple models are acceptable for publications or not? Just for knowing
This
the
is a
data?
demonstration and
Yes.
teaching. Because you have to show. So proper LCA, you need to go step by step. Because if you go by industry standard, there is the ISO 44044. They will go item by item. Have you followed? It is quite thorough.
No, actually, I believe the criteria to get at least should include.
This one?
No,
This one is kind of black box.
No, for actually
Proper
just
one,
at least
yeah.
criteria to get. At least criteria to get.
So you have to go like that. And you can see that I have got you see this sort of aluminum all around. That's our kind of calculated data, maybe at one stage. So for example, these sort of level of materials you might need. So steel making, clear, right? So you can see kilograms CO2 equivalent pattern on steel basis. So iron ore, sintering, blast furnace, oxygen furnace, casting, and that is it all. And then in the paper, we went in iron ore deep into because it was not interest. I'm not sure whether I have developed iron ore what here. So this sort of, for example, steel making more or less, it still is not good enough for journal paper. It more. So at the moment, yeah, I cannot show my, I think I can show that paper like this. published which year? Now, 2020 maybe, so that you can see. So here I say ECWW, this is embodied energy. So energy component. So iron ore and steel, aluminium, bauxite, mineral processing, and aluminium metallurgy. So in copper pyro, metallurgy versus metal extraction and refining, hydro. So this sort of comparison you can make. What is the upstream, what is the downstream, midstream, etc. and separately divide that. So with copper, looks like that mineral processing concentration is higher compared to pyrometallurgy because there is sulfur, they use as a fuel and that reduces the heat load. So whereas hydro is particularly, that's a different question. We will look at it. Sorry, this one I'm struggling to manage this. Hopefully that is okay. Can you see this? So left axis is million tons exported from, I believe, Australia, and right axis is the price per ton US dollar per ton of iron. And I was telling you that how that gone up 900 million plus in 2023. So when I started my career in 2010, we can see that nearly 270 ton to 900 million ton. Export value depending on per year, what's the price, because price varies, you get product. So basically, Australia is big, iron ore is big, or one of the major produce export value we get from iron ore. The second one is, this one is, global production. So a little bit I can go increase. So obviously Brazil, so that I said, what this one interesting one. What I compared, what was 1995, what was 2010, what was 2019. India is here or not? Number 4, I see, that's right. So you can see that 1995 to 2010 gone up and 2019 down, is it? Because that's I don't know, some reason.
Australia boom.
So, but anyway, that came from various so Brazil, Australia gone up significantly, and other countries. So, as a percentage of global, that goes up and down depending on production.
The Australian has gone up, so Indian will go down automatically.
Local market.
So, it's a percentage of global.
Percentage of, so once Australia's percentage goes up, the others will go down.
Others will go down.
That's why it has gone down.
Makes sense? Then last one, so you see,
Percentage.
so this is our iron ore model. That's drilling, blasting, excavating, loading, haulage, going down. Then lumps and fines, lumps takes another road, fines goes to another stockpile, this is our port. From mine to port and then shipped overseas. This is the visual version, we have got numbers, all the track kind of models we have.
So I don't know to oversee.
Yes.
That is the last point.
Last point for Australia. FOB comes. Three on board, and then you go to Japan, Korea, China. China is another
So you calculate up to your shipping point.
we have done also, that's I'll show you. So then each of these.
What is haulage?
Haulage is transport within the mine, dump. Loading and haulage, crushing, etc., screening. I'm not going to show everything, but what I'm going to show you. So that's a calculation procedure. Similarly, in inventory, you need to know. This is how you do your LCA. Basically, I'm showing how you calculate CO2 emission. So you can say that one. Even all these N4, you know that what is N4? Ammonium nitrate fuel mixture. So that's explosives. 94% ammonium nitrate, 6% fuel oil. And we need to know everything associated with that in terms of CO2 emission. So then energy, ECWW, I don't know here, it's mainly energy and global warming potential. So you can see that total is 12 kilograms CO2 per ton of ore and energy is 152 megajoule per ton of. So when you iron ore comes into the plant, that sort of it comes from Australia, that sort of loaded CO2. And you can see why they're coming from. And I told you yesterday that loading is one of the kind of bottleneck because you cannot have big dump trucks, usually dump trucks with the capacity. So the total is
Also add the CO2 emission to the transportation.
I have not included shipping yet, but I will show you shipping. So say this one is interesting figure, very interesting. I did myself. I know exactly. So what is happening here? Million tons. Australia produces 900 million tons of iron ore. So what I calculated, what is our CO2 emission from that? So whoever is taking it, making steel, that's also producing CO2, right? So that's all through. And that is drilling, blasting, loading, crushing, grinding, stacking, inland rail transport, onshore port operation, shipping you can see that one, shipping coal, shipping iron ore, shipping coal also included, offshore port operation, sintering, blast furnace iron making, obviously that's the culprit, basic oxygen furnace casting, so that's the way you can see up to that 1.5-ish. So that depends on, also the factors are there, it's a ballpark, it's maybe sometimes it will be higher, it makes probably.
It is still not great.
Still high.
No, it's not till catered to grade.
No, it's not catered to grade even. It's I think it's cast.
Cast, yes, cast. After that, once it's disposed of, then you get the complete one.
That's the complete one. Yeah, that's right. So I don't know whether I don't think this part of that.
Loading is not also not required.
So this one is the same graph by excluded blast furnace. Blast furnace component. So I think the point is that shipping is significant component. So shipping is significant component. That's what it shows. What else I had? I estimated. I think that's again shipping without. So that estimated greenhouse gas from Australian iron ore production for both and overseas steel, and what's the distribution of that? And you can see that shipping is probably quite a significant part. Loading, hauling, and shipping. These are the two areas. So I think that's what we say. But the other one, I don't be skipping that one because that's interesting. So I don't want to name producer 1, producer 2, producer 3, the 6 producers we looked at. How much I don't know, actually somebody look at the data, they can see which company is which. What is the potential crude steel from that ore? What's the energy used? What's the energy used in metal mining and metal? Emission for mining, emission for metal, water waste, I say CWW, and maybe CWW maybe. And so here, I shouldn't say that because we send the iron ore to someone else, we have some responsibility on that. So we can tell these countries, please reduce, because we are giving you the product, you should make it properly. And that's a liability of Australia in terms of value and solution liability. It's called extended responsibility of our resources. So if I go, it's not necessarily imposing anything, but in our country we are doing our best. But we are producing something, giving it to someone, and they are not very good. We need to have a responsibility to tell them, okay, do better or whatever way. So that's to show that what is our responsibility.
So 2.5 is actually your Australian producer.
Which one? The 6 company?
East one, 2.5.
Which one is that? You are talking about?
Last one.
Last one, producer 1. That's a small producer, 50 million ton. Yeah.
It is here in Australia.
Australia, it's all Australia.
And 90% is mainly in
Sorry?
India or China.
Yeah, that's right. Yes. So it's another way to see. I wish I can add more like that, and then also get back to that way. So that's another thing. This is what also interesting, that primary energy input per megajoule per ton or kilogram per ton of iron ore, that's a current, but theoretically possible if you manipulate all this stuff, there is significant reduction potential. And so carbon emission can also reduce if you manipulate some of the emission we made, that but theoretically we cannot get 100%. So maybe practical. What is practical? So in between sort of scenario, it could be the best practice. That's right. But still you can see that 43% reading, etc., but 71% crashing and drying. So significant reduction possible. So again, my point is that we do all sorts of things, investment, this and that, but maybe there are small low-hanging fruits. Let's look at that first. And unless you go through this kind of exercise, you cannot do it. That's what I get. Any question or comment? So have you done, are you required to do this kind of things at ESP plant or ISCO plant? Do they sort of auditing exercise or do what can be done as a low-hanging fruit?
Actually, we are process guys, so we do not do this kind of thing. But our energy department, management department does. They calculate the carbon footprint. They calculate the water also.
Do they share with you or what?
Yes, we get the monthly or annual reports, but I don't actually consider this LCA part of it. They will totally or not.
But ultimately, I think the process people are the main people who can implement the.
Yes, actually, we can give them a feedback that this is what we have learned.
Right. So, but on the other hand, what I'm saying that implementation is a your role, isn't it?
No, we can do one. From process point of view, we can do is that we can see that the process becomes more efficient. That is one area we are working on. We all are working on it.
That's right. Okay. So okay. So I think that's kind of food for thought, I guess. What else has to show? I think I'll tell Avash to copy these ones and then give to you. So you can pass on to your people also. That you feel free to. I think I've gone through that, but it is more life cycle assessment of various energy technologies. So, but I just want to show you that obviously, in the beginning I said why do we interpret it and all these 4 or 5 components according to standards, and then you what I going to say. So you see that one that each fuel has their own characteristics obviously, and CO2 emission from fuel combustion kilogram per gigajoule, and you can see the highest is coal, is it a black coal? Natural gas is low. Liquefied natural gas a bit more. Your petrol is high, diesel and fuel oil. So that's because the density different, heating value different, and obviously your carbon content different, your CO2 emission is different, right? And then each of these fuel we model for coal, for example, you have to mine it, you have to convey, crush, transport, and go to the electricity power plant, right? And then you have to do the same with gas. Right? This is natural gas, LNG. I think this is LNG. Simplified flow diagram. Then you have got crude oil, which is this one is desalting, refining. I think this is a simplified version of crude oil. Then I showed you this one, fuel consumption and fuel preparation and fuel combustion and total emission per unit. And so what we say here, I think that one we have responded. So if you say your fuel is coal, your technology is subcritical, supercritical, ultra supercritical, open cycle gas turbine, or closed cycle gas turbine, or diesel, or fuel. So you have got minimum, maximum, and conditions, and total as part of electricity production. That thing. Okay. So I think I tried to do sufficient conditions and try to do the last one. The 100 power station. So we have which one is high, which is low, the gas. It's beyond CO2. CO2 that one, but other impacts what they call that high coal something. So not necessarily one is other something because it's better for one or something is not better for something. And what that we can even health because so that's 100 megawatt. Coal is higher in health impact damage. before also. Got, so that's what I wanted to show. My lecture is what's left. I think last one is practice demo software. Okay.
So do you have other estimated greenhouse gas for charcoal production from biomass or something?
Yes, so that's the paper I mentioned, Journal of Sustainable Metallurgy. Go through that one. You have got the details and call me because you are connected with me. I can give you whole data set where you perform. Okay, it's easy. So now, so we have done fair bit. Any comment or question before I move into the software side?
This chapter you will share with us.
Yes, all I tell our student get from here. I don't know.
I think
It is something you don't.
I think you are audible without it also.
If I move that, so now the best part of this course is the software
application.
but sorry
हम लोग लाइसेंस
but what I require, you are lucky that I didn't force you to go through to learn the software. Part of the course I do that people practice software.
It's a difficult within these 5 days.
Exactly. So you will be feeling bored.
And it is a
For
paid
your-
software.
it's more good for the students. Generally, I
Paid
do
software,
say
कैसे use
master's
करोगे?
student, post PhD students. Students is good, and I force them to do that. And make it to the
So
same
the course duration will be longer in that because within 5 days I think it's difficult to
concentrate on the software. But so that's why I thought I spoke with Dr. Arup that this broad overview of what is happening globally in Australia, particularly focusing on hydrogen, LCA. It's maybe not you are doing day-to-day jobs, but maybe you can learn some flavor. So that was the last one. I'm not sure have I fulfilled more of this expectation. Okay. So now, so let's for software. I open that story. You see from the back it's a little bit tricky, but at least you can get a flavor for. So this is the same. I've got both softwares, but I will show you Sima Pro. So there is another software that's for experts. So I use. There are OpenLC also I have got. I would recommend you look at OpenLC. See that one? Sorry, not that one. So that's the software, okay? Sima Pro developer version. And I have got quite July until Sunday because it has to be updated every year. You need to pay a certain amount of money. So now, okay. So if I go fast, so you have got left Explorer window, right? So Explorer window, it has got the goal and scope description, those stages I talked about. You have to put that. There are lots of libraries. The heart of this software is this library, the database. And the database is the equipment database, food database, Australian life cycle inventory database, US database, Danish database, in every basically. There are so many databases. As a package, Indian database is not there, but some Indian data is there. I'll show you.
yeah, then industry 2.0
That's another kind of database. So industry data 2.0. So there are so many I have got. So the database is there. If I go back here, it's all about this kind of window is important. So before going there, also another thing, database, software should have database and methods. Somebody asks that what method do you use? Characterization factor. Which one you pick?
So we can additionally include additional database.
Also you can. Your own database you can.
Yeah, you can do that.
You can even feed Excel data file as an input.
It has a format of Excel.
Yeah. So I'll show you probably. So but essentially that this is a method and you must have a method and it's called recipe midpoint. It is a global method. There are Australian method, you can pick that one, that North American method, etc. But mainly global method people will say in this case I use, and endpoint, midpoint, I quickly resist that. I didn't go detail, but you can get a flavor for that. So method and database, these two things must be there in the software. Second thing is the processes. So as I said, so this is my processes. I have got materials, any materials you need, maybe there. If I say that materials, my materials, you can see agricultural materials, select chemical materials, have been acid, inorganic, organic acid, fertilizers, everything, okay? And then materials has got electricity by coal, I forget about that. You have got transport, all sorts of transport, road transport, rail transport, etc. Okay? There are 20,000, even 25,000 data points. They have got processing. Here you have got anything you want to process it, it's the metals. We have got metals, ferrometals and non-ferro. So I hope that metals has got, when I say it's not what, but if I say ferrometal will have steel in it. So the rolling is steel, etc. You can have some that's processing. Maybe materials has got more metals. Metals, if I click here, extraction. So metal ferro extraction, you can have stainless steel. So ferro extraction is steel, low alloy, various types of steel, chromium, etc. So you can have multiple sort of products. Okay, are you following me? Okay, so now let's stop that one. Go back to energy. So with energy, you have energy, electricity by fuel, electricity by country mix. So electricity by and heat also. Heat is energy also. So electricity by fuel, you see that one, biofuel, biomass, coal, and if I click coal, different types of coal, gas, different types of gas turbine, geothermal, etc. Photovoltaic, maybe wind is there, you see. So 1 kilowatt hour to power, water is required, etc. So that's all there. Okay. So now what I'm going to show you, maybe if I say electricity, right? Okay, let's look at the coal-fired power station. So coal-fired Australian coal-fired power station doesn't matter where you make electricity, it's the same. I'll just pick one. High voltage. So there are some Indian electricity. India, AP is what? Which is state to be?
Andhra Pradesh.
Andhra Pradesh. Maybe West Bengal. Let's look at because there is West Bengal. Why not? Rajasthan, UP, West Bengal. Let's look at data of production. This is simple. So this kind of that's documentation. Usually you can put a name, you can put your own data set. This is already there in the library. You can generate your own and you can copy it and put your own number. So that's, you see that unit process. Unit process means it's more detailed, whereas there is called system process, which is kind of black box. You don't have much detail. And then you can say that location data sets, etc. That somebody has collected this data over a certain period and has gone to be a review process. And they have the data, but still, because you guys work here, in the power plant exactly, hard coal power plant 100 megawatt such capacity. It is held for certain range, not everything. Okay, so that is very published. So then this column is or this sheet is very important. This is the input. So output 1 kilowatt hour electricity. To make 1 kilowatt hour electricity, you need water, you need coal. you need light fuel oil, etc. And then there are, decarbonized water, etc. Anyway, so that's, and also emissions, going to what kind of emissions going there, but all the details, CO2, etc. Now, if I want to calculate what's the effect of that, so I have to pick a method, and I pick method. So that's the recipe point page. Hope probably people are following. 1 kilowatt electricity. So my job is to generate a number 1 kilowatt hour electricity. And so I think that's what we've done enough, and I say calculate. You can say exclude infrastructure or not. So that kind of options are there. So it will be calculated for you. So this is whatever data is there. It doesn't matter really, I'm not assessed anything, but if you assess, you can generate properly. And if you say steelmaking, electricity is one component, you can have all other things that you develop the model. So I have got, for example, hydrogen model, I've got lots of different models here, various metal production. So that's the, you can see, if I go to network, I showed you probably that in one of the lecture that wooden shed LCA, how to do that. So this kind of network diagram is so you can see that one like that. So what it is saying, so this is a very simple process. 1 kilowatt hour electricity, high voltage, you can go 1.5 kilogram of CO2. And that is coming from mostly 0.7 kilogram coal is used, and that will generate that much. And also the coal looks like the main one. Mine, you go further down, you can go as a but in this case, that is a relatively small process it is. And then you can go to the network. Sorry, this is network. You can go to the table. So that table will show you all these values. And you can export it to your Excel and Excel file. All these numbers are, and you can generate compare number of processes. You can see that where they are. So that one is as a sort of graph. You can see. In this case, just electricity. That's why if you have multiple systems, then that column can be segmented into various things. So it's a kind of way I'm just giving you the flavor. But if you do more, it becomes quite handy tool to navigate that. So that's basically I wanted to show you a little bit. I'm not sure how we are going to time. Should we get a break? Maybe 5 minutes and come back and finish it off just in